Okay, so hello everyone. This is the live interactive session for the last week, that is week 4, for the course Introductory Field Structural Geology offered by NPTEL. My name is Rajiv Mukherjee and I am a Prime Minister's Research Fellow at the Experimental Rock Deformation Laboratory of the Department of Earth Sciences, IIT Kanpur. So this is the last class I will be hosting for the live session of this course. And this is the outline of the week 4's content of this course. As you have already learned about brittle deformation, measurement of strain through field observations, and finally summarizing the course about the regional deformation of Shingbum Craton and the Shingbum shear zone as a whole. And this was primarily done by culminating all the observations during the field work for the 4 week of duration. So as I said, this is the last class and this is 16th of August 2025, and this is the link to join the meeting. Hopefully we will be having another session for extended doubt clearing about the course before your final examination. Okay, so about week 4's content and the concepts that we learned was primarily about the concepts of brittle deformation, fracture mechanics, how we observe fractures in rocks and how we interpret them, and difference between fracture and a fault plane, identifying fault planes in the field, fault plane architecture, then identifying non-penetrative features along the fault surfaces such as slicken slides and slicken lines, etc. Then use of slicken lines and slicken sides in identifying the relative motion direction of the fault, and then observation of joints and shear fractures in the field, understanding the mechanics of conjugate shear fractures, interpretation of stress field orientations from these orientation of conjugate shear fractures, and then signatures of brittle ductile deformation in the field, observation and interpretation of the deformation mechanisms of tensile gash fractures, dike intrusions in metapelatic rocks, and reaction zone and baked zone deformation architecture surrounding the dike. Then structural features of a ductile shear zone, measuring strain from kinematic analysis of deformed tables and conglomerates in shear zones, strain analysis of deformed syn sedimentary structures, concept of 2D and 3D Flynn diagram for kinematic analysis, and finally overview of the regional deformation of the Shingbum Craton and the Shingbum shear zone. So with all of this, today's topic of discussion will be mostly related to the interaction about week 4 course content and answering any doubts, and then solving some conceptual problems that I have curated over the week, over the last week to match with the content that we have seen in week 4, and finally summarizing and concluding these live sessions. Okay, so let us start. So first question is about brittle deformation, and the question says, which of the following rock types are likely to be associated with joints? And the options are given as cerotachelites, migmatite, pegmatite, and aplite. So if you know the answer, you can obviously unmute yourself and say. Otherwise, I will give 1 minute to think about this question, and then I will obviously discuss what will be the correct answer for this question. Okay, so the likely answer for this question is option C, pegmatite, and I will explain why. So first of all, let me define the difference between a joint and a fault. Okay. So joint is a type of fracture fracture plane with negligible fracture parallel displacement. Okay. Therefore, joint planes can be inferred as static cracks. Okay. Whereas fault planes are fracture planes with, fault planes are fractures which experience considerable or appreciable amount of displacement along the fault interface. Whereas fault planes are fracture interfaces or fracture planes which experience appreciable amount of interface parallel displacement. Right. So obviously joint planes, although it is not um, although it is not a fault plane, it certainly can generate weakness within the plane, within the material. Joint planes can generate weakness within the material. Right. Now, because of this inherent weakness, the joint plane may or may not localize strain. Right. But joint planes do accommodate fluid intrusion in the host rock. Okay. Now, because of the fluid intrusion, hydrothermal fluid intrusions will produce an acidic environment with negligible differential stress. Okay. And because of that, large grain sized big minerals will be precipitated, will crystallize, and that will eventually form pegmatites. Right. Now, pseudotachelites, on the other hand, they are formed through extreme pulverization and frictional melting. Excuse me. And frictional melting. Right. So obviously, if pulverization is happening and frictional melting means you generate so much amount of friction that it will eventually heat up the material and partial melting will take place. So this obviously is associated with high displacement rate and high strain rate events. Joint is obviously a static feature, and pseudotachelite emerges from a very dynamic feature. Therefore, pseudotachelites are by default associated with faults. Right. And apelite is an igneous intrusion. And therefore, since joints are mostly late stage events, joint planes are mostly late stage deformation events, Therefore, applied cannot be associated with joint planes. Applied emplacement is unrelated to joint planes. Okay, so this is the reason why pegmatite is most likely the probable geological feature that can be associated with joint planes rather than having pegmatite or xerotectite or applied. So this was the first question, and now we can move on to the next question, question number 2. And it says that a rock mass in an area is faulted. The fault surface shows slicken sides. If the rake of the slicken lines is 90 degrees, then the fault is option A, strike slip fault, option B, normal fault, option C, thrust fault, option D, cannot be determined only from the rake. So if I provide an information about the rake of the slicken lines, then I can say that on a fault plane, the rake of the slicken lines provides the magnitude of provides the direction or the orientation provides the orientation of the net slip, which is then used to determine the trend and plunge of the net slip. So this is what is we can get. Now based on, so if I have a fault plane like this, and if this is the slicken lines, right? So this line is the net slip, this is the strike line, and this is the dip direction. Right, so this angle theta, it is the rake or the pitch, and based on the rake of the slicken lines or rake of the net slip, we can classify faults into 3 categories. Option A, strike slip faults. So in case of strike slip faults, the rake of the net slip is 0 degree. Then comes the oblique slip fault, where the rake of the net slip lies in between 0 degree to 90 degrees. And finally, deep slip fault. The rake of the net slip is 90 degrees. So since it is given that the rake of the Slicken lines is 90 degrees in this case, so we can say that the fault is a deep slip fault. Right? So deep slip fault can either be normal fault or it can be thrust fault. But other than that, we cannot further deduce what kind of fault it is, right? So therefore, given the options, best is option D. That is, we cannot be determined. So the nature of the fault cannot be determined only from the rake. So another thing which we can get from Slicken sites is that Slicken sites appear as distinct steps-like features. So if we know the rough direction, so the rough direction is approximately the direction of displacement. Right. But other than that, we cannot get extra information from these Slicken lines. So what are the required information other than the rake of the Slicken lines is required to actually know whether the fault is a normal fault or a thrust fault? So there can be at least three different criteria and three different required information. Number A, it can obviously be the structural discontinuity from the map. So if we just know which formation is going up or down, or the repetitive or the omissive nature, so that means the structural discontinuity is required from the map. This is first option. Second option is identifying the footwall and the hanging wall. So if we do not know for certainty which is the footwall and which is the hanging wall, it is quite difficult to establish the relative sense of motion, right? And finally, we require deformation signatures associated with normal faults and thrust faults. That means we have to go to the field and actually observe what kind of features we are getting. Deformation features associated with normal and thrust fault. So if we can deduce this information, then it is likely that we can answer what kind of fault it is, whether it is normal fault or a thrust fault. But only from the information with the rake we can say that it is for certain a deep slip fault and nothing more than that. Okay, coming up to the next question, which says, which of the following sequence of fault settings represents decreasing release of energy during an earthquake? Option A, thrust, strike slip, and normal fault. Option B, thrust, normal and strike slip fault. Option C, normal, thrust, and strike slip fault. And option D is strike slip fault, normal fault, and then thrust fault. So this is a good conceptual question. So I will pause for a minute to let you think, and if you know the answer, you can always unmute yourself and provide us with the answer. And if not, then we will discuss which is likely to be the correct answer in this case and why it is the correct answer. Anyone would like to try? So think in terms of force and displacement, because energy is the product of force and displacement. So if you keep the distance displacement constant, then obviously the larger the force required, the more the energy will be. It is obvious. Then in which case do you require the largest amount of force and the least amount of force? If you can know that, I mean, if you know the force, then you can also think in if you don't know the force, then you can also think in terms of the stress. So which requires largest amount of stress and which requires the least amount of stress. That's it. Okay, so option A is the correct answer in this case. That is thrust fault, then strike slip fault, and then normal fault. So this is how the energy will decrease from thrust to strike slip and then to normal fault. Why? Because normal faults in many cases are associated with gravity. And since it is gravity, that means a component is here and it has to be pulled down. That means the stress fields associated with a normal fault is similar to a tensile nature. Stress field can be of tensile nature. Okay. Thrust faults, on the other hand, works against or opposite to gravity. and therefore the stress field is obviously compressive in nature. Okay, and obviously the strike slip faults are associated with simple shear fractures, right? Simple shear fractures. And the stress field is related to simple shear. Now, force is basically stress times area, right? So if we keep the fault plane area constant, then energy is proportional to strength, stress or the strength of the material, right? And since compressive strength is greater than shear strength, which is greater than the tensile strength, and that is why thrust faults. So if I talk in terms of energy, the thrust fault energy will be greater than strike slip fault energy, sorry, and which will be greater than the tensile or the normal fault energy. So thrust and then strike slip and then normal fault, and as we discussed, option A is the correct answer. Okay, so moving on to the next question, question number 4. Choose the correct statement regarding the relationship between bedding parallel joint spacing, layer thickness ratio, layer length to thickness ratio, and the material stiffness. And the options are: highest stiffness and highest length to thickness ratio produces highest joint spacing, highest stiffness and lowest length to thickness ratio produces highest joint spacing. Option C: lowest stiffness and lowest length to thickness ratio produces highest joint spacing, and lowest stiffness and highest length to thickness ratio produces lowest joint spacing. So for joint planes, spacing between different joints, there are some set of joint planes, then one plane to another. For a joint set, the spacing let us consider del D is related to stiffness and length to thickness ratio let us consider this ratio R in the following manner. So del D is inversely proportional to stiffness and del D is inversely proportional to R. That means del D is inversely proportional to SR. That means if we just plot joint spacing del D in y-axis, so this will generate this kind of curve, right? So eventually for lowest length to thickness ratio and for lowest stiffness, the joint spacing will be higher, and that is how the mechanical layering is as well as the stiffness of the material is actually the controlling factor behind joint spacing in sedimentary rocks with bedding plates. So that is why option C is the correct answer. Lowest stiffness and lowest length thickness ratio produces highest joint spacing. Okay, so this was question number 4. Now move on to the next question, question number 5. It says that a fault plane has an attitude of 030 40 degree southeast. The attitude of the bedding plane in the host rock is 040 45 degree southeast. If the rake of the Slicken lines on the fault plane is 90 degrees, then the fault can be classified as option A, strike slip fault, option B oblique slip fault, option C trace fault, and option D none of the above. So if you think for a minute, I guess you can find the answer what will be, but don't worry, I will obviously discuss. So if we draw the stereo plot, this is north, east, south, west. So fault plane attitude is 030, 40 degree southeast. So this is 030. And then the host rock has 040, 45 degree southeast. Like this. Uh, So the intersection obviously will plunge towards east southeast in this direction. It can be at around 100 to 120 plunge direction. And since both of the planes has a dip amount nearly 40 to 45 degrees, therefore the plunge amount automatically will be within that range, right? Since both of the fault plane and the host rock bedding planes are almost parallel, the intersection lineation will be like plunge around 40 degrees and trend will be 100 to 120 degrees, right? And since the rake of the slicken lines is 90 degrees, the fault is a deep slip fault. Right. Now the fact is that since both the fault plane and the bedding planes are almost parallel, therefore the displacement along the fault obviously will be um, parallel to the bedding plane, traces of the bedding planes, right? And also since the lineations, the intersection lineation and the uh, this intersection lineation and the slicken lines, they will have a uh, they will have the same trend, right? Down deep lineation. So the trend of the slicken lines and the intersection lineation, they are parallel. I mean parallel in the sense they will have the same trend, and the bedding plane is almost parallel with the fault plane. So based on this observation, we can say that if there is a displacement, if displacement takes place along the fault plane, it will hardly be recognized. The offset will be hardly recognized because of the parallelism between the bedding plane and the fault plane. And that is why these kind of faults are known as trace faults, because the trace of the bedding planes are parallel to the fault planes, and trace of the bedding planes are parallel to the slicken lines. So that is why this is a trace fault, and option C is the correct answer. So if I write it down, since the intersection lineation since the intersection lineation is parallel with the slicken lines, which means the trend is similar, and the bedding plane is almost parallel with the fault plane. Therefore the fault is a trace fault. Okay, so this is the answer. Now let us move on to the next question. In an oblique slip fault having 30-degree dip, the net slip is 10 meter at an angle of 45 degrees to the strike of the fault plane. The deep slip component of the fault plane is the following meter. So you have to find the answer, calculate what is the deep slip component, the magnitude of the deep slip component for that given fault. So if this is the strike slip direction, and if this is the deep slip direction, then somewhere between these is the resultant net slip. And if we consider that it makes an angle theta with the strike slip, and this angle eventually is the rake of the net slip. Then following the trigonometric relation between net slip, strike slip and dip slip, we can write that strike slip is equal to net slip times sine times cos theta and the dip slip is net slip times sine theta. Right? Now given is that theta is 30 degrees. Sorry, not 30 degree, 45 degrees. So the net slip is given, the angle is given. We just have to calculate the dip slip component of the fault. So the relation is simply is this one. So we can calculate dip slip is equal to 10 meters times sine 45 degree, which is almost equal to 7.1 meters. So the answer of the question, that is how much is the dip slip, so it is 7.1 meters. Okay, so moving on to the next question. Dip of a fault plane is 30 degree. If the horizontal and vertical throw of the fault is 245 meters and 100 meters respectively, then calculate the net slip of the fault with the rake of the Slicken lines on the fault plane. Right? So we have to know how to calculate the different sections or components of a fault. So we have heave and throw. Heave is the horizontal offset and throw is the vertical offset that is produced because of the obliquity in the net slip. Right? So heave is always calculated on a planar section of the fault, and throw is calculated along the vertical section of a fault. So if we just talk about the vertical section first, So given the dip is 30 degrees, this angle is 30 degree. This horizontal component of displacement, this is heave, and the vertical component is the throw. And this one is the dip slip, right? So first of all, from this vertical section, let us calculate what is the heave. So throw by heave is tan 30 degree, and therefore heave will be throw by tan 30 degree. Throw is 100 meters, right? Because horizontal throw is 245 and vertical throw is 100 meters. So 100 by 1 by root 3. So it is nearly about 173 meters. So this is the throw. Now if we talk about the relation between dip slip and throw, we get that throw by dip slip is equal to sine 30 degree, right? Therefore dip slip is again throw by sine 30 degree. So 100 by half, which is 200 meters. Okay, so we got the dip slip and the heave. Now if we talk about the horizontal section, so in the horizontal section, this is the horizontal throw. This is the heave, and obviously this is the strike slip. Right? So the strike slip can be calculated from the Pythagorean relation, which is horizontal throw square minus heave square, which is 245 square minus 173 square, which is nearly about again 173 meters. And since we know the strike slip and the dip slip, we can calculate the net slip. Again from the Pythagorean relation, which is basically the dip slip square plus strike slip square under root, which is 200 square plus 173 square, which is fairly enough. It's around 264 meters. So this is the net slip amount. And finally, we can calculate the rake. How? Now we know that deep sleep is equal to net sleep times cos phi. Therefore, phi is basically cos inverse. Sorry, this is sin phi. So sin inverse 200 deep sleep by net sleep 264, and the value is 49 degrees. So this is the rake of the fault, and the magnitude of the net slip is around 264 meters. Okay, right. So this was question number 7. So let us move on to question number 8. So a pebbly conglomerate has undergone pure shear deformation under plane strain condition. How will the pebbles in that rock look like along the XZ section and YZ section of the exposure? Option A, linear along YZ section and circular along XZ section, circular along YZ section and linear along XZ section. Option C, linear both along YZ and XZ section, and option D, circular both along YZ and XZ section. So anyone would like to try the answer? Okay, so imagine this is the XYZ coordinate. Now we are assuming that the table was originally a sphere, right? Now, if it is deformed, then obviously it will take an elliptical shape. So after deformation, the pebble takes an elliptical shape. So in terms of kinematic framework, the long axis of the elliptical pebble will be the x direction. Intermediate axis will be y, and the short axis will be z. Right? So in that case, this is how the pebble will look, right? Now if I cut a section from xz like this, so say for example xz section, right? This one. So if I cut a slice along this, what I will find, it is extremely flattened. And if I cut a section like this, which is xy, I will find elliptical shape, right? And if I cut along yz, that means this part. So I am basically chopping off the ellipse from the center, and since at the center of the ellipse it is almost cylindrical, therefore if we just cut along yz section, it will appear almost like a circle, right? So this is how different sections will appear, and therefore option B is correct, because along yz section we can see a circle, and since the since so this is basically x is greater than y greater than z, so this is the framework we are following for kinematic analysis. And since x is very greater than y, and which is also greater than z, so if we cut a section across the xz plane, we will definitely find that it is almost appearing as a line. So we will get circular section along yz and linear section along xz. Now Question 9 says that the mineral lineation observed lying on the axial planar cleavage of a regional fold in a ductile shear zone will likely plot on the dash, excuse me, domain of a three-dimensional Flynn diagram. Option A, constrictional domain. Option B, plane strain domain. Option C, flattening domain. Option D, either constrictional or flattening domain. It can lie on the both. So, how ductile deformation in the folding in a ductile deformation can take place. So let me start with simple schematic diagram. This is a layer which is stage 1. In stage 2, you compress the layer, so it will initially suffer some homogeneous shortening. In step 3, it will create folds. Right? This will be the axial planar cleavage. And keep in mind, lineations are parallel to the lineations are on this axial plane. So in stage 4, this doesn't happen like this, but if we just compress enough and then start shearing, so if this is the stage 4 of a ductile shear zone, so we have started shearing these folds after their compressed, simultaneous compression and then shearing. And eventually, if we continue this long enough, we can gain something like this highly sheared structure. Folds are extremely compressed and we are getting shearing with this kind of compressive forces all around. So it is getting thinner and thinner, and the axial planes are now almost subparallel to the horizontal direction, and so is the mineral grains or the mineral lineation. So therefore, if we just now see along the Flynn diagram, right, so this is plane strain condition, then comes flattening, and here is the constriction. So obviously the lineations which will be forming lying on the foliation axial planar cleavages, which has experienced extreme shear localization as well as folding, will obviously be plotting in this flattening type region. They're extremely flattened and stretched. So option C is the correct answer, that these kind of lineations will definitely plot on the flattening domain in the three-dimensional Flynn diagram. Okay, so moving on to the next question. Question number 10. If x, y, and z corresponds to principal axis of strain, then choose the condition most likely that would result in formation of folded chocolate tablet boudinage in a single deformation event. Option A, x is greater than 1, y is equal to 1, but z is less than 1. Option B, x is highly greater than 1, y is equal to 1, and z is highly less than 1. Option C, x is highly greater than 1, y is also highly greater than 1, but z it is highly less than 1. And option D, none of the above. So this is a question related to the chocolate tablet boudinage formation. And this is how it looks. Right? So we get the boudinage limb, thicken hinge, and they appear like Kit Kat bars. Right? So these are just like chocolate bars, and that is why they are called the chocolate tablet boudinage. So it is kind of a signature of a transtensional deformation. We have shearing, folding, and then tension developed along the limbs that are getting stretched, and therefore we are forming boudinage. Right? So as you can see in the strain ellipsoid here, this is the x direction. So x is likely that it is very, very greater than 1. And if you just follow, everything is getting flattened across this fold, and that is why you are getting thickened hinge. Right, so that is why you're getting the thickened hinge, and that means y is also stretched equally, and that is how individually the aspect ratio is maintained. But then again, to actually keep the material's volume constant, it is not like a material it will be gaining volume. If the volume has to be conserved, then there has to be some tearing to accommodate the strain, because at some point of time it is not enough for the material to flow to be thin enough to maintain the volume. So initially what happens is, because of extreme flattening, these are getting stretched and the z is consequently becoming lesser and lesser than 1. But at some point of time it is not enough to make the material thin and also flow along the x and y direction. At some point there has to be some discontinuities, and along that discontinuity the material breaks or tears, right? So that initiates fracturing. So it is obviously a sign that y is also very, very greater than 1 in this flattening domain, but then z has to be very, very less than 1 in order to conserve the volume. And this is how in the flattening domain one should get these kind of signatures, that is x is very, very greater than 1, y is also very, very greater than 1, but z has to be very less than 1 in order to maintain the volume, and also producing these brittle deformation signatures that is known as the folded chocolate tablet boudinage. So option C is the correct answer in this case. Okay, so moving on to the next question. Question number 11. A strain ellipsoid of a deformed rock has the principal axis of strain identified as ABC. The stress ellipsoid for the same rock mass has the principal axis of stress as P, Q, and R. Which one of the following option is correct in terms of stress and strain? It is given that A is greater than B, is greater than C, and eventually P is greater than Q, which is greater than R. Option A is to P, B is to Q, and C is to R. Option B, A is to Q, B is to P, and C is to R. Option C, A is to R, B is to Q, and C is to P. Option D, A is to Q, B is to R, and C is to P. So let me write that A is essentially lambda 1, or the elongation axis of the strain ellipsoid, so which represents the direction of maximum stretch. And hence minimum shortening. B is equivalent to lambda 2, direction of intermediate stretch, which represents intermediate shortening. And C is lambda 3, which represents direction of minimum stretch, which represents maximum maximum shortening. Yeah, right. And also the fact PQR, they are essentially sigma 1, sigma 2, and sigma 3. So you should know that lambda 1, lambda 2, and lambda 3, they are collectively inversely proportional to sigma 1, sigma 2, and sigma 3. And therefore, maximum compression creates minimum stretch, right? That means sigma 1 is proportional to lambda 3, right? And minimum compression creates maximum stretch. So sigma 3 is proportional to lambda 1. So P is equivalent to S and R is equivalent of C. Sorry, P is equivalent. P means sigma 1, which is related to lambda 3 means C. Sorry, it will be A. Is C and this will be A. So P is equal to C. So A is equivalent of R and C is equivalent of P, and therefore option C is the correct answer, right? A is equivalent to R, B is equivalent to Q, and C is equivalent to P. Okay, so that is how a stress ellipsoid and a strain ellipsoid are related to each other. So moving on to the next question, question number 12. Shortening of the Earth's upper crust is accommodated by folds and joints. Option B, normal and reverse faults. Option C, folds and reverse faults. Option D, folds and normal faults. So shortening requires compressive strength, compressive stress regime, right? So structures that form in compressive regime are folds and thrust faults. Or reverse faults. Because normal faults, as we have seen, it is not related to compressive regime, and therefore option C is the correct answer, because folds and reverse faults or thrust faults are only formed in the compressive regime, and that controls the shortening. So option C is the correct answer. Okay, moving on to the next question. Two planes having attitude as 04590 and 13590 intersects each other. If the value of the maximum, intermediate and minimum stress in that region are 45, 32 and 18 MPa, having plunge amount of 0 towards 002, 90 towards 270 and 3 degrees towards 097 respectively, then calculate the maximum shear stress acting on these two planes. So if we draw the stereo net, this is north, east, south, west. So one plane is 04590, that means it will be like this. Another is 135, exactly 90 degree to this one. So this will be like this. So the north, the south, and east west are the acute bisectors. One of the stress actually have plunge amount 0 degree towards 002. So this is one. Another has 90 degree towards 270, and 90 degree means it is exactly at this center. And another one has 3 degree towards 097, somewhere here. So this one, which is 45, this is 32, and this one is 18. So this is obviously sigma 1, this is sigma 2, and this is sigma 3. So these are the orientation and the magnitude of the stresses. So as we can see, sigma 1, sigma 2, and sigma 3 are perpendicular to each other. So I mean, the thing is that the stresses, we are not, so the information is not given in the sense that these are the principal axis of stress. It has generally been given as 3 stresses. They have a decreasing order of value, and it happens to have that they are also perpendicular to each other. So this is 90 degree, this is 90, and this is also 90. So the stresses have a decreasing order, of magnitude, and they are also perpendicular to each other. That means sigma 1 is 45, sigma 2 is 32, and sigma 3 is 18. So these are principal stresses. We can identify that. And for maximum shear stress, half times sigma 1 minus sigma 3 into sine of 2 theta, which has maximum value equivalent of 1, and therefore maximum shear stress tau maximum is half times 45 minus 18, which is roughly around 13.5 megapascal. Right? So this is the maximum shear stress acting on these two planes. These are the joint planes. So these are the conjugate shear fractures or joint planes. And their experiences, they have experienced this much amount of shear stress. Okay, moving on to the next question. The relationship between X, Y, and Z of deformed pebbles in a conglomerate and the axial planar cystosity is such that on S1, that is the axial planar cystosity, X and Z of the pebbles always lie. Only X of the pebbles lie. X, Y, and Z of the pebbles lie. And option D, X and Y of the pebbles lie. So this is a diagram of a ductile shear zone. This image was illustrated by Professor J.P. Bourg. So in this case of a ductile shear zone, the kinematic frame of reference is that always the lineations are parallel to x and then they have the y plane. So the shear plane is always the xy plane, right? And since axial planar cystosity develops parallel to shear planes, therefore the foliations are, the S1 planes are the shear planes. And since it is the shear plane, which is xy plane, then obviously the pebbles will have the x and y pebble, x and y directions of the pebble will obviously lie on the shear plane, and that is why D is the correct option, right? So the next question says, a schist represents a material which has a mechanical property as homogeneous and isotropic. Option B, homogeneous and anisotropic. Option C, inhomogeneous and anisotropic. Option D, inhomogeneous and isotropic. So it is quite easy that foliations are anisotropic planes. So they have a directional anisotropy. Directional property. So layer perpendicular high strength, layer parallel they have low strength, and this layer parallel strength, I mean for a particular layer, if the rock type is homogeneous, then for a particular layer the mechanical property along that layer is also appears to be homogeneous. So if the composition remains homogeneous, then only anisotropy exists along two particular directions. So therefore schist always represents a mechanical property which is homogeneous and anisotropic. Compositionally homogeneous in terms of layering, I mean each and individual layers are homogeneous, but then again because of the layering there is an inherent anisotropy in terms of their mechanical strength. So option B is the correct answer. Now moving on to the next question, it is quite easy. So if a rock is subjected to a constant strain rate of 1 in 10 to the minus 15 per second, calculate the value of stretch and quadratic elongation over a duration of 100 million years. So it is just simple calculation, is that you have given strain rate, which is the derivative, time derivative of the strain. Therefore the amount of strain is nothing but the strain rate times the time derivative. Therefore the total amount of strain will be the integral of strain rate and the time derivative, which is basically strain rate times the time. And eventually the total strain is um, in the form it can be calculated in the form that, so if we just know the total strain, we can calculate the stretch. So the stretch is basically 1 plus epsilon, and then the quadratic elongation is 1 plus e, sorry, 1 plus epsilon square. So that is how we should calculate the value of lambda. Now we need to calculate what is epsilon in this case. So it is 1 into 10 to the power minus 15, the strain rate, times the duration, 100 million years. Now 100 million years is, if we express that in terms of seconds, so 1 day or 1 year represents 365 times 24 times 3600. This much amount of second per day. This much amount of second per day. This is the amount of seconds per year, and 100 million year means 1 million year is 10 to the power 6, and then it is times 100, which means 365 times 24 times 3600 whole to the power 8 raised to the power 8 is the duration of 100 million years. And if we just calculate 365 times 24 times 3600 and then raised to the power 8, it is nearly about 9.78 times 10 to the power 59. It comes like that, 10 to the power 59. So the amount of strain will be eventually 1 into 10 to the power 15 times 9.78 into 10 to the power 59. So it is 9.78 times 10 to the power 44. This is a huge amount of stress. It is absurd amount of stress, right? So which tells us that calculating the strain just by simply multiplying the strain rate with the time is not the correct approach, right? And that is why complex rheology or complex rheological calculations are taken into account in order to estimate the true strain accumulated over the time. Just because strain rate is not enough to calculate the strain, it is required to know about the initial configuration of the material, particularly the thickness or the aspect ratio over which the deformation is taking place, right? So when these parameters are known, along with the strength of the material, like the Young's modulus or the stiffness or the Poisson's ratio and the viscosity, then we can apply certain rheological models to correctly estimate what would be the future strain accumulated over these 100 million years. And Once we know that, then we can certainly apply these formulas to actually calculate what will be the quadratic elongation in that case. Right? Okay. So the next question says, choose the correct answer. Option A. In progressive pure shear, all material lines rotate during the course of deformation except those parallel to principal axis of strain. Option B. In progressive simple shear, all material lines except those parallel to the shear plane rotate during the course of deformation. Option C. The terms irrotational and coaxial are not synonymous, neither are the rotational and non-coaxial deformations. And option D. All of the above statements are correct. Now, it is evidently option D, because during progressive pure shear, that means you are, so if this is progressive, so for example, this is your initial sphere or circle, say for example, and you are compressing it along y direction. So for pure shear, what will happen? It will be flattened out like this. So any line which was initially parallel to y and x, they will remain perpendicular to each other. But any other line, say for example, if I draw line like this and this, because of this rotation, they will rotate. I mean, because of this compression, these lines will rotate and they will eventually form like this, except for the lines which were initially perpendicular to each other. That means they are the principal axis of strain. They will not change or rotate. So option A is definitely correct. Option B says, in progressive simple shear, all material lines except those parallel to the shear plane rotate during the course of deformation. So if I have a box, say it's a square like this, and if I shear it, you can see that it will look like this. So this is the shear plane. And the line hasn't shifted from there, but except for the fact that which was initially vertical, it has rotated to some extent. That means any material line which is parallel to the shear plane will not rotate and remain the same, but all other material lines will change or their orientation or rotation in case of a progressive simple shear deformation. Right? So that is how option B is also correct. And since this is a coaxial deformation and this is a non-coaxial deformation, these two terms are not equal, and neither is the rotational or irrotational are same. So irrotational and non-coaxial is not synonymous, because this deformation is obviously coaxial deformation, but in this case also there happens some rotation of the material line, whereas rotational and non-coaxial also not related. The non-coaxial means the axis of the strains will change due to progressive deformation, right? So in case where the strain axis itself starts to rotate, right, then it becomes non-coaxial deformation, but that doesn't restrict the rotation. Rotation can also even occur in coaxial deformation. Not always all the rotations occur along non-coaxial deformation. So that is why these terms are also not synonymous. So option C is correct, and that is why the actual correct answer will be D, because all of the above statements are correct. So coming to the final question, question number 18, which says that a foliation plane strikes north 40° east. The apparent dip of this foliation plane is along north 10° east, and the apparent dip amount is 30°. If the dip of the foliation plane changes to 60 degrees during another phase of deformation, then calculate the amount of shear strain suffered by the foliation plane. So we have the apparent dip, say this is so the apparent dip amount is given, which is 30°. The trend is 10°, right? And the strike is 40°. So therefore, the structural bearing will be strike minus trend, 40 minus 10, that is 30 degrees. And if true dip angle is delta, then tan of apparent dip is equal to tan of true dip times sine of structural bearing beta. Therefore, true dip delta will be tan inverse of tan 30° by sine 30°, right? And that is around 49 degrees. So the final dip of the fault, dip of the plane is 60°. Therefore, the change in dip angle is 60° minus 49 degrees, which is equal to 11 degrees, right? And since this angle is shear angle, which is equivalent to the shear angle, which is 11 degrees, we can calculate the shear strain gamma as tan of psi, which is actually tan of 11 degrees, which is almost equivalent to 0.19. So 19% shear strain will occur if the dip amount of the foliation plane starting from 49° changes to 60 degrees. Okay, and with that I end today's discussion session for the course Introductory Field Structural Geology. This is the last discussion session. Hope you have learned a bit about some conceptual problems, numerical questions, how to tackle them, and some new formulas to calculate structural attributes and their trigonometric relations. Hopefully there will be another extended doubt clearing session within 1 or 2 weeks, and for another 2 hours we will so if you have any other doubts finally going through all the lecture materials of this over this course of 4 weeks, we can have another discussion session. and after that you will be appearing for your final exam. So all the best for your examination for this course, and with that I am ending this discussion session. Thank you and bye.